Hello and welcome back to part 2 of our discussion on Taylor series, sections 9.9 and 9.10. In this second video, we're going to continue the discussion of the 9.9, 9.10 handout, exactly where we left off previously, where the previous point where we left off was at the bottom of page 6, where we were entertaining a question about limits. The interesting thing about Taylor series is that effectively what they're doing is they're encoding derivatives over and over and over again as you take more and more terms of your series. As a result, there in the background there's actually hiding some application of L'Hopital's rule, which makes determining limits that are otherwise indeterminate a lot easier to compute. So take a look at this limit right here. Notice that if I were to just plug in 0, I would simply get 2 times cosine of 0 is a 1, so that's 2 minus 2, that's a 0. Parenthetically, this is equal to 0 over 0. And so what that means is you'd like to use L'Hopital's rule. And you could, but the point is we'd like to highlight an alternate way that uses Taylor series in order to accomplish this task. And when the limit here is approaching 0, what that means is it can sometimes be useful to use a Maclaurin series. Let me show you what I mean. I'm going to build a Taylor series for this entire limit function, where the only object I don't really know all that well is the cosine, but the cosine itself has a Taylor series. So notice that this limit is the same as computing the limit from x goes to 0 of 1 over 3x to the 4th times x squared minus 2 plus 2 times the following series. This is the Maclaurin series for cosine. I'm simply going to use negative 1 to the n times x to the 2n over 2n factorial. Where I can clean this up a little bit, I can expand this cosine series. So if I just copy this and paste it right here, what I'm going to do is I'm going to erase this series expansion. I'm actually just going to write it out. This is going to be 2 times. The series for cosine is going to be a 1 minus x squared over 2 factorial plus x cubed over 3 factorial, only evens, x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. The key observation here being with this expansion, we see that this 2 will cancel with the first term of that series. And when I distribute this 2 onto the second term, the numbers are going to cancel, and then this x squared is going to cancel with that x squared term, leaving me with the limit as x goes to 0 of 1 over 3x to the 4th times. This 2 is still going to distribute, and so I'm going to end up with a 2 over 4 factorial x to the 4th minus 2 over 6 factorial x to the 6th plus 2 over 8 factorial x to the 8, etc. Where now this coefficient in front starts to distribute, and I'm left with now the limit as x goes to 0 of what? I'm going to get 2 over 3 times 4 factorial. Notice that the x factorial here and the x factorial here will cancel. Whereas otherwise I'd get x to the 6th over x to the 4th, which will leave a surviving x to the 6th. This will be minus 2 over 3 times 6 factorial x squared plus 2 over 3 times 8 factorial x to the 4th, etc. And the key observation is that this term, and all future terms, all of these terms have x's in them. Which means as I take the limit as x goes to 0, all of those terms themselves are going to go to 0, with the stark exception of the first term, which has no x in it. So therefore, that first limit is the term is the only one that survives, and this limit is equal to 2 over 3 times 4 factorial. Now, you can verify, if you go all the way back up here, you could verify that by L'Hopital's rule, you could verify that this is equal to a 2x plus, well, I guess it would be a minus 2 sine of x over a 4 times 3 is a 12x cubed. This is still going to be indeterminate, so you have to do L'Hopital's rule again. And you're going to get a 2 minus 2 cosine of x over, this will give me a 36x squared. This is still indeterminate, so you have to do L'Hopital's rule again. And then you're going to get a simply positive 2 sine of x over, what does this become, 72x. It should go without saying I do need to have my limit as x approaches 0 here every single time. I can't be forgetting that. We're going to copy that and insert that in each of these. This is still not appropriate, so I have to do not determinate. So I have to do L'Hopital's again, and I get the limit as x approaches 0 of, now I'm going to get 2 cosine of x over 72, and now I'm finally not indeterminate, and this will just give me a 1 on the top, and this answer is 2 over 72, which conveniently matches what we had down here, 2 over 3 times 24, which is 2 over 72. So indeed, we are getting the same answer. The only difference is I didn't have to L'Hopital 4 times in a row to make it happen. So this is an interesting example that showcases our ability to use series, or the Taylor series, to determine limits we didn't otherwise have the ability to compute. This is maybe a complicated answer. We can take a look at some simpler answers. Like here we have x goes to 0 of sine of x over x. This is another thing that's classically L'Hopitalable, but we can do with series instead. This is the same as the limit as x goes to 0 of sine of x over x, which is 1 over x times the series from 0 to infinity of negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial, which this is going to be the limit as x goes to 0 of, well, let's write out a few terms of this. I'm going to get 1 over x times, what do we get here? We're going to get now, this is an x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x, etc., right? And the key thing here is when I distribute by this 1 over x, every single other term will have an x in it, but the first term won't. So it's exactly the same situation as before. Here we're getting the limit as x goes to 0 now of 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial, etc. And so each of these terms is going to go to 0, and the only survivor is in fact 1. Which you can confirm via Calc 1 techniques or by using L'Hopital's rule that this limit is also a 1. So we are indeed getting the same answer with that we would get with old techniques. But this is not always, you don't always have to restrict to limits at 0. We could do limits, say, at 1. Notice if I take the limit, it goes to 1, I'm still getting 0 over 0, so it's still indeterminate, parenthetically. And so I could do L'Hopital's rule, but the whole point of this conversation is that Taylor series can make L'Hopital's rule not necessary. Now I will say this, There are instances where you cannot use L'Hopital's rule computationally, and so that's why this technique exists. Unfortunately, we're not going to be able to go deep enough into the concepts to highlight those differences, but if you were to continue down certain engineering tracks, you'll find that this approach to computing indeterminate limits is the computationally cheaper option. So that's why we're discussing it. Back to this problem at hand, though, when the limit here is x goes to 1, what this means is instead of using a Maclaurin series, you want to use a Taylor series centered at x equals 1. This is going to be a problem here because the ln function, if we use our cheat sheet, well, our cheat sheet only has Maclaurin series, so certainly it's not centered at x equals 1, which means we actually have to figure that out first. Note that ln of x, if we add and subtract 1, we're going to do a 1 plus x minus 1. Now remember, of course, Taylor series centered at 1, this means a series of the form x minus 1 to the n. So if I add and subtract 1 algebraically, this is already a 1, so I don't have to sort of split it with properties of logarithms. It's already a 1. Now I can use ln of 1 plus a thing to turn this into its series from n equals 1 to infinity of, this is going to be negative 1 to the n plus 1 times x minus 1 to the n over n. This is a Taylor series centered at 1, so this is the correct expansion to use for the numerator's ln. Thus, if we want to compute the limit as x approaches 1 of the ln of x over x minus 1, this is the same as the limit as x approaches 1 of 1 over x minus 1 times this series, which I'll write out a few terms of. This is going to be, let's see, at n equals 1, I'm going to get x minus 1. At n equals 2, I'm going to get a minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus etc. And we see we're in the exact same position from before. Indeed, as we distribute, notice that each of these terms is going to have a surviving power after we do this nice distribution. It's going to have a surviving factor of x minus 1, which means when we take the limit as x goes to 1, each of these individual terms are going to go to 0. And the only survivor we get is the limit as x approaches 1 of just 1, which turns out to be the limit. And we can verify using L'Hopital's rule up here that this would have been equal to the limit as x approaches 1 of 1 over x over 1, which is of course a 1. So yes, I agree with you if you use L'Hopital's. Oh look, it's so much faster. Like I mentioned though, this technique is a computationally cheap alternative because L'Hopital's rule is a computationally difficult thing if the derivatives of what you're looking at are somewhat complicated. Of course, the derivative of these, very straightforward. So we have two more examples to take a look at, and basically they're just variants of the same limit question. The only difference is the objects that you can build Taylor series out of are a little bit more complicated. So in this case, we have sine x minus tangent x. And in this case, we have the limit as x goes to 0 of 1 over sine x minus 1 over x. The key thing here is that things like tangent and things like sine x, or 1 over sine x, which is the cosecant, these don't have normal Maclaurin series or Taylor series. And the question is, can I still compute their limits? Well, it turns out the answer is yes, you just have to be willing to expand a little bit. So, for example, this is the same as the limit as x approaches 0 of sine of x minus, well, we'll say sine of x over x cubed minus sine of x over x cubed cosine of x. And so if you're going to write it all this way, what you want to write out is the following type deal. If we write the limit as x goes to 0, we're going to have first 1 over x cubed times sine x, which we know is just x, minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, etc. Minus, well, the top is a sine, which we know is exactly the same thing. And the bottom is an x cubed times a cosine, which is a little different. That's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. And the key is that after we write all this out, we can start trying to simplify a little bit. This becomes the limit as x goes to 0. But what happens when we start distributing here? We're going to end up with, let's see, a x 1 over x squared minus 1 over 3 factorial plus x squared over 5 factorial, right, etc. I guess this should be a minus. Minus, well, what's going to happen here? Notice that we could, for example, if I embed this x cubed up here, what we're getting is we're going to get a x over x cubed, which is going to be a 1 over x squared. And then if I embed the x cubed into the rest of all of this, it'll simply reduce the powers. So we're going to get minus 1 over 3 factorial plus x squared over 5 factorial, etc. Divided by, then we just get that cosine, which is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. And so what we see here is we have the following. We have a bunch of terms that are going to go to 0 in the limit. All of these are going to go to 0, go to 0, go to 0, go to 0. We have two survivors, which is this number and this number. And then what we see is that as x goes to infinity, in some sense what's going to happen is that this number and this number are actually going to end up canceling. So I think maybe the easier way to see this, well, no, I think that's a perfectly valid way to argue this. So in the technical way, you'd have to do long division between these two things on the right. And then as you build long division, what you'll see is that there will be a constant term in the middle, in the front, and then there will be a bunch of terms with x's after that, and each of those will go to 0. And there was a homework problem last week that had you take a look at the series for tangent for the first couple of terms, and that would be useful in this case. So you'd have to do the long division between these. But essentially what's going to happen is that there will have this survivor on the left, there will be a survivor on the right, and those will combine in a way to create your final answer. So reference the tangent and then work through this in a little bit more detail. I think maybe that would be the correct way to proceed. But I don't remember exactly. I don't have enough space here to redo the tangent computation. So definitely re-reference what we talked about last week in that homework problem. So we'll put a ... there. And the last problem that we want to take a look at is a very similar problem here. Here what we have is if I were to, say, get a common denominator here, this would be the limit as x approaches 0 of x minus sine of x over x sine of x, which if I were to import what I know about sine of x, right, what I know about sine of x is that it looks like this. So I'm going to import that as the series representation for sine. And this limit is going to become the limit as x approaches 0 of x minus sine of x over x times sine of x, which if I were to simplify this, notice that the two x's up here will cancel, and so this is going to become the limit as x approaches 0 of, as I distribute that negative, I'm going to simply get x cubed over 3 factorial minus x to the 5th over 5 factorial, etc. over, I'm going to get x squared minus x cubed, nope, x to the 4th over 3 factorial plus x to the 6th, can't count, over 5 factorial, etc. And now the key thing here is that I can factor out the highest powered term in both of these. And what I'll end up getting here is the limit as x approaches 0 of x cubed times 1 over 3 factorial minus x squared over 5 factorial plus etc. all over x squared times 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial. The x squared and the x cubed will cancel and leave just an x upstairs. And so this will be the exact same limit except for just an x upstairs. And the key element here is very similar to the previous one. Everything with an x will, of course, go to 0. And the only thing left now is going to be an x over two things that don't go to 0. So this is quite literally the same as a limit as x approaches 0 of just x, which is just good old 0. So that's going to be our answer. And so this is sort of the process we're talking about. It's the very same process we've been doing. When there's quotients, it's really no big deal. You just pull out as much of the common factor as possible, cancel, and then take a limit in the same way we did in Calc 1. And this is very similar to the structure of what will happen up here if you take a series, the first couple terms for tangent instead. Okay. But this is going to be sort of where we're going to wrap up the conversation on sequences and series. This is how we can use Taylor series to compute limits of indeterminate forms without using L'Hopital's rule. This is going to be all of our conversation on sequences and series. I know that this was a lot for us to learn, and all of you are doing a fantastic job of working through and getting comfortable with a lot of this information. As you have more questions, of course, I'm happy to answer them. Study hard to practice for the associated assessments on the Taylor-Maclaurin series. And I will see all of you next week, where we will begin a new journey going through Chapter 10 of the textbook, which will have us taking a look at parametrization of curves, polar curves, and a really cool set of items that involve drawing pretty pictures with petals and roses. But until then, take a look at the homework, let me know if you have any questions, and I will see you all next week.